So a line integral, recall from last time, is an integral where you're integrating over a curve of some sort. They call it a line. Well, it could be a line, but it could be something else, not just a straight line. And so there are going to be three different kinds of line integrals that we're going to be doing in this class. And you will get all three of them on quizzes and exams. So be prepared for any one of those three. So the first type, which I call type 1, which technically is a scalar line integral, a scalar line integral. What is a scalar line integral? It's a line integral that involves a scalar function. And in this case, typically it's like a density function for a wire, because this first type of line integral, the best real life application is finding the mass of a wire. Okay, so the idea is you're going to be given some vector valued function describing your curve, and it could be a 2D or a 3D vector valued function. And hopefully they'll give you some time interval for that curve. And if they don't give you the vector valued function and they just sort of describe the curve in maybe as a function of x or function of x and y or something else, you have to go parameterize it and figure out on your own what the time interval is. And your parameterization needs to match the curve and the orientation exactly. If it does not, I basically take away pretty much all your points. Okay, even if you got lucky and your answer was correct. Okay, so once you are asked to do a line integral, which generically will have one of these looks to it in the definition, you'll be given integral with a C down here. That means it's a line integral. And then you'll have some function, and then you'll have little ds. Little ds means arc length element. So when you convert one of those line integrals to an integral that you can actually work on, a regular single integral, you put the limits for time on your integral symbol. You rewrite your density function and replace any x's and y's with the x of t, y of t, so something to do with time t, from your curve. And then you create your arc length element, which is basically speed, which we learned like 2 months ago. It's the magnitude of velocity. And then you integrate with respect to t, which typically represents time. So your integral, once you do convert everything to t's, better only have a t's in it. If I see x's and y's still left over in one of these integrals, you blew it. You blew it. So be careful. So we did an example, and now we're going to do some more examples. Okay, here we go. So I'm going to have you do an example shortly, so be ready. So this letter B, you're evaluating a line integral, and they're giving you some density function, if you're going to think of this as mass of a wire. And then little ds, that's the arc length element. This C down here means you're going to be doing a line integral. Now, they're not telling you the vector valued function this time. Like the previous example I did Wednesday for you, that was real nice because they gave you the R of t and they gave you the time interval, and they just handed it to you on a silver platter. And you're probably not going to get that lucky on an exam or a quiz. So be wary. So here they are giving you a picture of the graph of the curve. It happens to be a straight line. And you go, oh, man, okay. Well, good news, because I already taught you how to parameterize a straight line, like 2 months ago. If you're given 2 points on the line, you can create the direction vector for the line. Remember this? And get the parametric equations. And we'll just take those parametric equations and jam them into a vector valued function. Great. So if you recall, the direction vector here, if you call this first origin as point P and the other point here Q, the vector PQ, 1 minus 0, 2 minus 0, 1 minus 0. Okay, so we're doing terminal minus initial, and there it is. And then, if you're going to just get the parametric equations, pick a point, and I'm going to pick just the 0, 0, 0. And then your direction vector is giving you the coefficients of t. So obviously this is parametric equations, but you're just going to put that into a vector valued function. Now, the only thing that's missing for me, because I'm going to dock you big time, don't assume that I know what the time interval is. What time interval is going to work that's going to match this line segment exactly. I want it to match. I want it to start at 0, 0, 0. And then, and see this arrow, it tells you the direction. I got to go in that direction and end up at the point 1, 2, 1. So what's my time interval? From what seconds to what seconds will match that line? Anybody know?
0 to 1.
0 to 1 will work. Very good. So now that you have the parameterization for your curve, you can now do all that needs to be done to get your line integral converted to a regular single integral. So you're going to want to get your velocity vector, of course, and then your speed, which is the magnitude of velocity. And in this case, it's going to turn out that the speed is a constant. Is that always the case? No. We just got lucky here. So now when you convert this line integral that they gave us here to a regular integral, you're going to go, okay, 0 to 1, because that's your time limits. And then the arc length element, the ds, is going to be square root of 6 dt, right there. And then you're going to need to convert the function that they gave you, which in this case was x squared minus y plus 3z. I don't want to see x's and y's and z's in this integral here. I need to only see the t variable. Oh boy. So what do I replace x's, y's, and z's with? Anybody have an idea?
Can you use the line equations that you formed?
Okay, so what do I, so instead of x squared minus y plus 3z here, which I don't want, what am I going to replace the x squared with?
T squared.
Yeah, this is going to be your x. You'll replace all the y's with 2t and all the z's with t. You use your components from your original vector valued function. Okay, so I'll have t squared and then minus y, so that's minus 2t, plus 3z, so plus 3t. That's what's going to be the density function basically converted to t. Now I can add some like terms here. So really, I only have to integrate t squared plus t. And this square root of 6 is just a multiple, so I'm just going to throw it out in front of the integral. I can do that. And then the limits are 0 to 1, and this is a super easy calculus 1 integral that I think everybody can do very quickly, so I'll just do it really fast. And then I'll end up with, square root of 6, 1/3 plus a half minus 0. And then the exact answer is 5 square root of 6 divided by 6. Okay. Now, what if you had parameterized that straight line differently? Because we learned a couple months back that parameterizations are not unique. You could come up with a perfectly legitimate parameterization of this straight line. Like, remember how I used the point 0, 0, 0? Heck, I could have used the point 1, 2, 1 here in my parametric equations instead, and that would have been legit, right? That's a nice parameterization of that line. That's just as valid. Would I get a different answer for my line integral or not? Does anybody want to? I'm not saying you necessarily would know, but
I think you would.
okay. So do you think it'd be the same or do you think it'd be different?
I think it'd be different.
You think it would be different? Okay, that's fair. George says different. Anybody want to challenge that?
Probably be the same because the curve is fundamentally the same.
Okay, who's saying that? Allo? Okay. So Allo is going up against George here. Interesting. Well, this isn't a democratic thing here, so I'll just tell you, it doesn't matter. You can, as long as the parameterization is an accurate one, it's legit and actually matches your curve, believe it or not, the line integral result will exactly match. They'll be equivalent.
Oh, you got me, Aloe.
Yeah, all right, well, all right.
That was just a
Alan,
guess, man. You did better.
it's just a guess, right? You know, no test here, no judging. Okay, so as long as the parameterization is a match for the curve, believe it or not, the outcome of your line integral will still be the same number. Cool. Okay. So let's, ooh, did I go past this? That's letter B. What's my letter C? Oh, this one is kind of cool. So we're going to evaluate this line integral. Ooh, now this is hard. And this is the kind of stuff I put on quizzes and exams. Okay, so listen up. Why is this hard? Because the last two were super easy. I usually don't give something that easy on a quiz. I just did that to boost your self-esteem. Okay, so why is this one hard? Because it's going to be a piecewise smooth curve. It's going to have different parts to it, different pieces. So they're telling us the curve, this curve C, is C1 union, that's a union symbol, C2. So it's created by unionizing two separate curves. Okay, so let's look at each of the legs of the journey, if you will, if C is our journey. So the first curve, the C1, is going to start at 0, 0, and it's going to go to the point 1, 1, 1 along a straight line. Ooh, in that direction. Remember, vector valued functions, when you graph them, have an orientation. Now, C2 is going to be the curve from 1, 1. So it's going to start here at the 1, 1, and it's going to go back to the 0, 0, but along a different path, people. It's going to go along the graph of y equals x squared. So y equals x squared is going to be a little lower than the y equals x. You can graph these. So this is going to be C2, and it's going to go along the y equals x squared graph. Okay, is everybody clear on how this curve rolls? In other words, the path is, you start here at the 0, 0, and you go along the C1, and then you hit the 1, 1, and then you come back to where you started, but you come back along the curve, the parabola y equals x squared. So there's two pieces to it. So how the heck do you do this line integral? So the idea, people, I know some of you aren't going to like this, is it's going to take some work. This line integral, you're going to have to actually do two separate line integrals and add the results. Okay? So your first line integral, and I'm putting C1 down here because you're going to do everything you need to do with the C1, parameterize the curve, do all your due diligence with that scalar line integral, get some number, and then add that to do the line integral all over again, but for the second curve. I know. Yeah. Okay. Now this is where it gets a little dicey. So let's see here. So let's do this guy first. Let's work on that. Okay. So we want to work on that. So how do you do it? Well, first of all, I need to parameterize C1. And good news, C1 is just a line, straight line. And you could do it the parameterization way by getting a direction vector and all that. I'm going to skip that and do it a little quicker. The quicker way is I taught you how to parameterize a couple of two-dimensional vector valued functions back when we were doing vector valued stuff in chapter, I forget what the number was, 13. But if you have a function of x, which y equals x is a function of x, you simply let x be equal to t, and then whatever y is, and then blah, blah, blah. In this case, y is just equal to x, so y is equal to t, fine. And now you got to tell me the range for time. What is time doing on this interval? So it starts at the point 0, 0, and then travels along the straight line and stops at 1, 1. What's my range for time here? What's going to make this happen? If t, t are my components.
0, 1.
Very good. 0 to 1. Fantastic. All right. So I got the 0 to 1. And now if I'm going to do this line integral, I do have to get speed, because that ds is arc length element. This is your arc length element. So you always have to remember that. If you forget that, I don't even give you credit at all for your line integrals. Seriously, I might give you a point or two if you parameterize the curve correctly. I'm going to go, yay, you parameterize great. There's a point or two. And then you forgot about the arc length element. Yikes. So your arc length element is always your speed dt here. So you're going to go, all right, whoops, I need to get my, sorry, let's get r1 prime. So what is r1 prime? What's my velocity vector? Well, take the derivative of t, take the derivative of t again. And so now when you get your arc length element, you're going square root of 1 squared plus 1 squared dt. Oh man, that's easy. That's just going to be the constant multiple square root of 2. Fine. So now what? So this line integral c1 x ds is going to be turned into, converted to a regular integral that we all can do business with, 0 to 1, because we said so. And then instead of the x, you're going to write what? What do you replace x with?
T.
Yeah, you steal the x component from your vector valued function. In this case, it's just t. And then your ds this time is square root of 2 dt. And this is pretty easy to do the integration. And I get square root of 2 over 2. Okay, fine. Save that for later because that's not the final answer. Why not? Well, we got the other leg of the journey there. We got to start at the point 1, 1 and go back to the point 0, 0 along y equals x squared. Now you have to be really careful here, because when you parameterize this curve, you have to parameterize it where it starts at 1, 1 and goes back to 0, 0. If you parameterize it and it starts at 0, 0 and ends up at 1, 1, you're going backwards. So I'm not okay with that. So this is the part that gets a little tricky. So I claim that even though y equals x squared is a function of x, normally you'd go, okay, just let x be equal to t, then y is equal to t squared. But this won't work because if you let t go from 0 to 1, this is going backwards. This is starting at the point 0, 0 and ending at the point 1, 1. So be careful. I'm not going to be okay with that. I'm going to dock you big time. Later on, I'm going to let you have time go backwards if we're doing a different type of line integral, but we're not. So what we're going to do here so that we make it come out is that I'm going to let x be 1 minus t. And then since y is equal to x squared, I'll just take this x, 1 minus t, and square it. Now here's the question. What are the limits for time? Remember, I want to start at the point 1, 1, and I want to go back and stop at 0, 0.
0 to 1.
0 to 1 will work here because of the way I've set up my components. So if I plug in the point 0, I hope you can see that both of these components, 1 minus 0 is 1, 1 minus 0 squared is also 1. So it will begin at the point 1, 1. And then when I stop at time t equals 1 second, substitute 1 second into these components, and you'll see that it'll end up at the point 0, 0. Cool. So now you can get your R2 prime, and this is pretty easy. I'll use the chain rule for the second component, 2 times 1 minus t times -1, like so. Yay. And then my speed is going to be R2 prime. So I'll do my arc length element here. R2 prime's magnitude dt, and that's going to be, oh boy, that's not going to be pretty. The square root of -1 squared plus, and this is -2 times the quantity 1 minus t squared dt. I could multiply all this stuff out, but I'm purposely not going to. You'll see why in a moment. And let's continue on the next page because I've run out of room again. Oh my goodness. Okay. Yeah. Okay. So, okay, keep in mind, so here I'm doing the C2. So this C2 x ds is going to become the line integral going from 0 to 1. I replace x with something. I have my arc length element, which is that nasty radical. And then what do I put here for x? Anybody have an idea? Do I just put t?
1 minus t.
Yeah, you got to be careful. You don't put t this time. The x component for your vector valued function R2 is 1 minus t. So that's what gets substituted for your x. Oh, is this even integrable? This is a hot mess, right? Anybody have any ideas on how to take the integral of this? Or should I just go to some computer system or you?
Rule.
Factor out the radicand and maybe use u sub for 1 minus t, possibly.
Okay, that's one strategy. I think U sub is gonna be what we are gonna need for sure. I would go with that. So the question is, what if I let U be equal to the radicand, like this whole mess here? What would happen if I did that? Let's just try it out, you know? Well, all it could hurt us. We could go, oh man, we screwed up. Let's stop and reevaluate. If you get du, the derivative of 1 plus 4, 1 minus t, the quantity squared, and you're going to use the chain rule here. How about 8, 1 minus t to the 1 power times the derivative of 1 minus t, there's that chain rule, negative 1. And then if I just rewrite this a little bit, okay, do you see something cool is happening? The power rule is going to work because I do have a 1 minus t in the integrand already. The only thing I need is a negative 8, and that's easy. You'll just put a negative 8 in here, provided you divide out by a negative 8, and then this looks like a nice power rule problem, right? Hey, who would have thought that would have happened? Cool, cool beans, as some people like to say. Yeah. And so I'm just going to go ahead and use my U sub, and then I'll do a little bit of reducing here. And then I'll back substitute for U, which was, oh man, it was that nasty thing. And I'm going to evaluate this mess between 0 and 1. You got to be careful because 0 here isn't going to make everything go to 0. So watch yourself here because that could be a disaster. So I'll keep the 1/12 out, and then I'll plug in the 1 first. And then I'll plug in the 0. Don't forget these 3 halves. A common student error. I'm just telling you after all my years of teaching. Common student error is they do all the work and they get there. They even say the right antiderivative there. And I give partial credit. And then they choke the rest of the problem because when they're so quickly, oh, I know what I'm doing now. And then they forget the 3 halves power. And then, oh man, all hell goes that. This is a 0, but there's still a 1 here. And then this is going to be just a 1 plus 4 to the 3 halves. Ooh, that's kind of gross. That's just 5 to the 3 halves. Yeah, okay, fine. So I'm just going to leave it as negative 1/12 times 1 minus 5 to the 3 halves. That, believe it or not, that's a positive number. And the approximate answer is about 1.56. And that would represent the mass of a wire that has this weird shape to it that kind of bends around on itself. Okay, questions?
When you were finding the parameterization,
I forgot something. Hold on a minute. Sorry to interrupt you. I forgot. This is not the final answer, right? Oops.
We had them, right?
We forgot something. What is our this is part of the answer. What's the final answer?
That plus
square root
the square root
2
of 2
over
over 2.
Remember that square root of 2 over 2 from the first integral, and then we're going to add it to this mess here, and then we'll get our final answer. Sorry. So that was, and I know this is like, oh man, that's gross. I think my math lab will accept something that nasty. And then this sum is 1.56. Okay, George, go ahead. You said if you were parameterizing something.
yeah, if you're parameterizing, when you were parameterizing the second like parabola thing,
Yes.
Is that something that you kind of just had to know that it was 1 minus t, or is there more
you kind of have to get the flavor, and sort of like the rule of thumb. And you could read my book for another perspective of this if you bought my book on Amazon, where you kind of look at t versus x. But another way to sort of figure it out easy is like, well, I got to start at 1, 1. So how about if I could just go 1 minus that t instead of just t? That's a
Okay.
good place to kind of always go from. Does that help? Like if we ended up just say at the point 2, 4, then how about let x be 2 minus t?
Yeah.
Does that
Yeah.
make sense?
Yeah, it makes sense. It just sounds to me like I just need to practice, basically.
Yeah, I know it's kind of weird to get your mind around here. But I'm going to give you some good news when we get to the other kind of line integrals that I will let you do. And some other professors don't, just to let you know, because they kind of want you to honor always having time moving forward. And when you're doing these scalar line integrals, you need to have time moving forward. You have to have time going from like 0 to 1 seconds, not backwards from 1 second to 0 seconds. But I will allow you, if you're doing a type 2 or type 3 line integral, to have time moving backwards because it'll end up being the same. Okay. So I'm just giving you a seed for later. Okay. All right. Are you guys ready to try one? But here, hey, good news. You won't have to parameterize. Okay, George? Good news. I've already parameterized it for you. Okay. And I've given you the interval that time is doing. So how hard could this be? And here's the density function. Now I am going to give you a hint. Please listen to my hint. I don't give hints, like I'm not trying to mess you up. Please distribute the 1 over square root of 2 before starting the problem, okay? Otherwise, you'll end up with the wrong answer, and then you're going to get all upset, even though you've done everything correct procedurally. And then you're going to, get, tears and all that stuff, and we don't want that to happen. Okay. So let me put you into some breakout rooms, and when your room opens up, please go in there, and then I'll come and visit and give you a hand, okay? Good luck. Bye. Well, let's just double check that we are. So if you took my hint, and if you didn't, then you wanna get that R of t is cos t over square root of 2 sine t over square root of 2 t over square root of 2. Fine. And then since I already parameterized it for you, because I gave you this parameterization, you don't have to worry about finding that whole mess. You're just going to go, okay, the arc length element is going to involve the velocity vector. So let's just go ahead and get the velocity vector. Okay, negative sine over square root of 2 for the first component, cos over square root of 2 for the second, and then just 1 over square root of 2 for the last component. Yeah. And so Nick, what album are we talking about? 6 hours of
After hours, I'll tell you.
Okay. So you got to get your arc length element. So let's go get the speed. And so if you take the square root of the sum of the squares of your velocity vector and do all the little arithmetic it's gonna take, and then oh come on Microsoft. Well, I don't know what's going on there. Okay, so I'll get sine squared over 2 plus cos squared over 2 plus a half. So this right here, if you factored out a half for the first 2 terms and then just went, oh yeah, sine squared plus cos squared, well, obviously that's a 1. So then you just have a half plus a half under the radical. Oh my goodness, that's just a 1. So square root of 1 is 1. Oh man, does that always happen? No. Don't get too excited. But when it does, it's like, hey. So then the mass is simply going to be this line integral. But that's going to be the regular single integral going from 0 to 6 pi of 1 plus, what do we replace the z with? What do you substitute in place?
One over the square root of 2t.
Yeah, you definitely want to use the z component from your vector valued function. So t over square root of 2 goes there. And then your arc length element just happens to be a 1. And then you have dt because you're always going to integrate these guys with respect to t. And this is super easy to integrate. Come on. I just get what? T plus 1 over square root of 2. Oops, 1 over square root of 2. Sorry. I'm going to write too fast. And then t squared over 2. And then evaluate this whole mess between 0 and 6 pi. So you should get 6 pi plus, and please mute yourself over there. I hear a lot of static. 6 pi getting squared over 2. And then this ends up being 6 pi, weird number, 6 pi plus 18 pi, this is squared, over square root of 2 after I reduce everything to lowest terms, okay? And if you whip out a calculator, it's approximately 144.47. So a mass of a wire should always be positive, okay? So if you are trying to calculate a mass and you get a negative answer, you know, hey, that's a little red flag there. You probably did something wrong. Okay, any questions on that? Everybody good with scalar line integrals? I haven't asked you to parameterize yet, so that's going to be the true test.
So just quick question, Resky.
Yeah.
When you're trying to determine how you should put your t in for your the function inside the integral, you just look at the variable and then determine it accordingly. So
Yeah,
this
you
would go
just you
z.
cherry pick whatever that coordinate was from the appropriate component from your original vector valued function.
All right, thank you for the
So
clarification.
just as an example, like what if instead of 1 plus z for your density function, what if they had, I'm just making something up, 1 plus yz or something weird like that, y times z. What would you substitute instead for your radicand here? You'd have 1 plus what?
Well, you'd have 1 plus cosine t over square root of t multiplied.
Careful, cosine, no. The
Oh, sorry,
y,
I was looking at the
don't look at the
prime.
don't look at the velocity vector. That's going to screw you
yeah,
over.
it's sine
Yeah.
t
Yeah.
over radical 2 t over radical 2, and they're being
Right,
multiplied.
right, yeah, exactly. Does that help?
Perfect, thank you.
Okay. Any other questions?
Nope.
Okay, good. Now let's get to type 2. All right. Scalar line integrals are good as they go, but truth be known, they're not as common as the other two types. Because traditionally, when physics folks do line integrals, they're operating in the world of vector fields, and they use them to calculate work done. So let's do a little bit of review. All right. So we're going to look at line integrals of vector fields, which is the next two types. And so we're going to look at this work done by a force field, vector field, as it operates in an object that's moving through the field. And I call the type 2 line integral the FDR version, not Franklin Delano Roosevelt, but you'll see in a moment why I call it the FDR version. Just bear with me, okay? So let's do some review. In the first chapter that we covered in this course, we actually did visit the concept of work. Remember I had that horse and we were trying to figure out the work done on that piece of granite is the you and the, whatever we're tugging on the rock. So we're going to do a similar thing. So let's just do a review. So this is just a repeat of the lecture I did a couple months ago. So let's say you have a big rock and it's sitting here with the front part at point P, and you move it with some force in the direction of the ground, and it ends up over here at Q. So the baby work formula, W for work, is just you're taking the force and you're multiplying it by the distance that the object moved. And so if the object doesn't move, no work is done. Like if somebody said, well, what if I were tugging on the rock, with all my might and I was burning up a lot of calories, but the rock didn't move an inch? How much work it has done? 0. Well, wait a minute, I did a lot of work. That's a different thing. We're talking about the work done on the rock. The rock doesn't move, no work is done. So you need some distance to be involved when you're calculating work. So for this little baby example, you would take the magnitude of the force and you would multiply it by this distance between P and Q, which would be the magnitude of the vector PQ. Okay, now the reason why this is not a good work formula to use, and we went over this, I did this is a review of my lecture, is this only works if your force vector is acting in the same as your line of motion. So the motion here was along the ground and the force vector was actually parallel to the ground. So the force acts in the line of motion, and that's very rare. Usually you don't get that lucky where your motion, your direction of the motion is the same as your force. So don't use this formula, okay? It's bad. Well, what's the more typical formula? Well, more typical, let's do the rock again. He's sitting there at point P, is the force is not going to be exactly in alignment with the direction of your motion. So let's say the rock still ends up over here. So your motion is along the ground, but your force vector is making an angle of, say, theta with the line of motion. So now you're going to project the force vector onto the line of motion, in this case, the ground, and then multiply it by distance, which is still going to be the magnitude of the vector PQ. And then we already did this formula where I did projections and all this, and this ended up being cos theta, magnitude of F, a magnitude of PQ, which was simply the dot product of the force vector with the vector PQ from our knowledge of finding angles between vectors. This was the formula, that theorem, and you could use it in reverse and get the dot product. So that was the whole point of all of this, okay? So now what? What does this have to do with what we're doing right now? Well, here's a picture of what we're going to be doing right now. You're going to have some vector fields. Remember, vector fields are collections of arrows, whoosh, you know, whooshing. Maybe it's a spinning like a spinning wheel, or maybe it's, you know, who knows what the vector field's doing. Okay. So it's got a bunch of arrows. And let's say you have an object. So the force vectors in this case are all kind of going that way. But let's say an object like a fly is flying around here along this curve. What's the work done on the fly as he, you know, goes along that curve? Well, you're going to use projections, because the only force that will actually contribute to work done is force that's acting in the line of motion. Otherwise, it's not contributing. So you're wanting to project all these force vectors onto the curve. Well, how do you do that? Well, you know, one thing about curves is you can get a collection of tangent vectors. So, you know, I'll just draw a bunch of tangent vectors here. In particular, big T, which is the unit tangent vector. And if you project the force vectors onto the unit tangent vectors, that will be the component of force that's acting in your line of motion and contributing to work done. So let's just look here. If I project, say, one of those force vectors onto one of those little unit tangent vectors, what do you guys know about projections? This is good review for the final, because you're going to have projections on the final. So remember, you take the dot product of the two vectors, you divide by the dot product of the vector that you're projecting onto's dot product with itself, or the same thing is the magnitude of it squared, but you're going to get the same thing, okay? That's a scalar times a vector, but the vector is the unit tangent vector because you're projecting onto him. Now, because the unit tangent vector, and the key word here is unit, has a magnitude of what?
1.
1. Then the magnitude of t squared is 1. So this just ends up being f dot t, which is some scalar, times the tangent vector. But then what is the magnitude of the projection of f onto t? And that's kind of what I'm doing over here. But that's going to be equal to the magnitude of f dot t multiplied with the unit tangent vector, okay? But that's going to simply be the absolute value, if you will, of f dotted with t times the magnitude of t, but that's just a 1. And typically what we do here is we go, all right, well, we'll just, we'll assume this is positive, and we'll go with that. So what you're going to see here is you're going to see F dotted with T, that projection of the force vector onto your unit tangent vector. So now if you're going to figure out the overall work done on the object as it moves, you know, all these little unit tangent vectors and so on, we're going to do a Riemann sum here. So I'll do a penumbra of a proof. Look at a little increment of work along a little increment of length of your curve. So delta S sub I is a little tiny arc length. And so your delta W sub I is going to be force times distance. So you're going to have your force, which is your vector field evaluated at some x sub I, y sub I, z sub I on your curve, dot product with the unit tangent vector evaluated at that point, x sub I, y sub I, z sub I, times a little tiny arc length, because that little tiny arc length is the little distance that your object moved. And they're telling you that x sub I, y sub I, z sub I is just a little point in your ith subarc. So then the total work done, the total is going to be the sum of all these little subarcs. So it's going to end up being a line integral. And it's going to end up being a line integral of the dot product of your force vector with the unit tangent vector, and then the little arc length element. So that's basically force times distance. But then here's the, I'm going to kind of abbreviate the F and the T just to be a little bit less bulky with the notation. And now here's the part that's the magic. Watch this magic happen, people. This is so cool. You're going to love it. And you have to come this far to understand what I'm about to do in about 1 second. You wouldn't have been able to understand what I'm doing without taking this whole entire course. Okay, here we go. Do you guys remember how to get the unit tangent vector? This is good review for the final. Like if somebody gives you some vector valued function, R of t, what would your unit tangent vector be for the R of t? This is good review for the final.
The components of R of t divided by the magnitude of R of t.
You're close, but be careful. I'll give you a hint. Unit tangent vector.
Or prime t.
It's the unitized
Or prime t
velocity
over.
vector. Remember, the big T is the unitized velocity vector. Please remember this for the final, people. You know, don't leave free points on the table, right? Okay, so there's your big T from a couple chapters back. Well, maybe 3 chapters back. Holy guacamole, we've come a long way, people. Congratulations. And then what about your arc length element? What did we get done in the last half an hour? What's your arc length element again?
The distance formula.
Yeah, but no, I don't want to go do it all over again.
Speed.
Come on.
You see the
That's
velocity.
how you derive it.
The
But now you
magnitude
know
of
what an
R
arc
prime of
length,
t.
what is the arc length element? Come on, people. We just did a whole bunch of crap here.
Speed.
Look. Here's a previous example. What did I tell you your arc length element is?
Magnitude of R prime of t dt.
Yes, thank you. Okay. Oops, I better not. There we go. Okay. So don't forget your arc length element. Now, I'm going to put that like as a true false. You know, yeah, I'm going to put true falses on the midterm. Hell yeah. So you better know your stuff. That's how I'm going to really find out. And if you don't have a legitimate mathematical argument to back up, you just like, oh, I'm going to guess. That looks true. And then I don't give lucky guesses, you know. Tell me why. Or, oh, it's false. Okay, tell me why. So your ds, your arc length element, is the magnitude, you know, of the velocity vector, aka speed. And then, of course, we're going to have a dt here because we're going to ultimately integrate with respect to t. Now, here's the cool part. This is cool, people. Oh, my God. You should just be amazed. This is going to happen. It's like, oh, my God, this is awesome. So the speed is going to cancel. Ah, ha, 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 ha. Why? Well, big T, he, you know, is a unitized velocity vector. And so he had the magnitude of velocity there, aka speed. And then the arc length element had speed inside. And so then what? So I'm going to go one more step before I get to our definition here. I'm going to use a little bit of different notation. I'm still going to have F. I'm still doing, this is supposed to be a dot product in there. That's a dot product. Dot product. Dot product. And R prime, I'm going to just use a different notation for R prime, if you don't mind, dr dt, dr over dt, the differential format. And then we still have a dt here. And then the dt's cancel. Ha, 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 ha. And we end up with what I told you, the Franklin Delano Roosevelt, FDR, line integral. Not really, I was being facetious here. So here's the definition. You've got a continuous vector field defined on a smooth curve C given by a vector valued function R, where time goes from A seconds to B seconds. Then the line integral of the vector field F on the curve C is given by FDR, which is the same as we saw the dot product of F with the unit tangent vector times the arc length. But usually you don't use that. I'm just doing that as an intermediate step. And then when you turn this into a regular single integral that you can actually do business with, you're going to iterate, you know, put the limits on A and B, the time, and then F, your vector field, will usually be given to you with X's and Y's or X's, Y's, and Z's, depending on if it's a 2D or a 3D vector field. But you're going to replace X's, Y's, and Z's with something that functions of T. So once again, you'll just cherry pick off your vector valued function, the corresponding X, Y, and Z components. And then you are going to take a dot product. Yes, you are. You better know how to take a dot product with your velocity vector. And then you'll just integrate that with respect to time T. Ba-boom. And there you have a line integral that you can actually evaluate. Okay, so let's do an example or two. Yay. It's not that hard. Okay, like I was in a breakout room and a student mentioned, hey, you know, this is a lot more fun than doing like double and triple integrals. And I go, yeah, it is a little bit easier, that's for sure, because double and triple integrals can be a little problematic if you have to be the one to put the limits on there and figure out the region and all that stuff. This is not as bad, okay? But I don't want you to get lulled into a false sense of, oh, this whole chapter is going to be easy peasy. It's not. It's going to be somewhat of a rear end kicker. So I just want to warn you in advance. I don't want you to get like, oh, you know, things are fine. Okay. So let me just see something here. Wow, that's really weird. Okay, so let's do an example. You hear some weird noises? Does everybody have a weird noise going on here? Is that me?
I have no clue. It just sounds like someone's serving a really mean tennis stroke in the background.
Okay. Does everybody else have a problem with the sound right now besides Nick?
I don't hear anything.
Is everybody okay? Isaiah says no, he's fine. Okay.
I'm going crazy. Great.
Let's just see some other people in the room. I don't know. Rick, are you there? Rick, Nicholas Gonzalez, do you have a problem with the sound? Are you guys okay?
I'm good.
You're good. Nick, are you Nick Gonzalez there? I'm just talking to you. Are you hearing okay? I'll check the chat in case you don't have a mic. Augustin says no prob. You got tennis courts. Nick, you're okay. Okay, thanks, Nick. Lizette's fine. Jordan's fine. I don't know, Nick Attaway. I think it's your end. You got some weird problems over there. Okay, I don't know.
Nothing I'm not used to.
Go talk to your neighbors. Maybe they're just making some weird noises. Okay. All right, so here we have a vector field. Okay, fine. So what? Well, we're going to find work done by this vector field on a little particle. Could be like a fly or a bug or, you know, some object as it's moving along a helix. Ooh, helixes are cool, man. The helix actually kind of looks like a slinky or a coil, like it looks like this. So there's the fly. He's going, okay. And you want to find the work done on him as he's like going around that spiral, starting at the point 1, 0, 0, but ending at the point -1, 0, 3 pi. Now, before I start this problem, good news, we don't have to parameterize because that still could be an issue here. They gave you the vector valued function. Thanks, guys. Here's what they failed to give you. They did not give you the time limits. Well, yeah, they did. They gave you a starting point and a stopping point. Yes, thank you so much. That's a starting and stopping position. So they gave you a starting position. Thanks so much. Congratulations, you have a starting position, but that's not helpful for what time it is. And then an ending position for the little fly as he's buzzing around. But that, you know, it's like, thanks guys, you gave me the starting and stopping position, which is not real helpful because I need the limits on time. Like, what time is it at the starting position? Like if I check my watch, you know, time equals 2 seconds or something. And what time is it when we stop or the fly stops? So how are you going to figure this out? Now, this can be kind of hard depending on the problem. Here, what you're going to do is you're going to look at the vector valued function, and you know, you want cosine to be 1 at when it begins and cosine to be equal to -1 when it stops. Similarly, you need sine to be 0 when it starts and sine to be 0 also when it stops. Okay, fine. And then look at t here. One of the components happens to be time t. Oh, we're in luck because they're saying t starts at 0 and then stops at 3 pi. Now, are these problems always going to be that easy? No. A lot of times, none of the components will be exactly t, and you may actually have to solve for t like 3 times and make sure that your time is exactly some, you know, that, you know, corresponds to that starting position coordinates, and the ending time corresponds to all the ending coordinate positions. So it turns out here, since one of the components, we're in luck here, was exactly time t, we'll just look at the starting and stopping for that. And so there's our starting and stopping time. Great. So why do we need that? Because the work done, people, is going to be a line integral of the force vector dot product with the velocity vector. And if we're going to actually turn this into a regular single integral, we need to know what time is doing on that interval. So 0 to 3 pi. And then you are going to do a dot product here. So I'm going to set it up. What do I put here for the components for this vector? And then this vector, what the heck? So let's fill in the blanks, shall we? Let's do this vector first, because this vector over here, the second one, is easier because it's just going to be the velocity vector, which, you know, they gave you the vector valued function, cos, sine, and t. You just go take his derivative. So I guess I'm going to have negative sine for the first component, cos, and then the derivative of t is 1. Fine. That was fine. Now, what about the vector field? Like, I get students who do this. Don't write this down, people. They go, oh, yeah, -1/2 x, -1/2 y. What am I doing wrong? 1/4. I don't want to see x's, y's, and z's in my line integral. You got to kill those guys off. Well, what do you replace them with? Anything I want? No, not anything you want. So what do you think?
It's RT components.
Yeah, you're going to use the R of t components. So any instance of x that you see, you'll substitute a cos. Any instance of y will get substituted with a sine t. And any instance of z will just substitute a t. So that's how you rewrite your vector field. So, and this, you want to do it before you do the dot product, otherwise it can get kind of messy. So here, my -1/2 x, I'm going to have -1/2 cos for the first component. And then instead of -1/2 y, I'm going to write -1/2 sine. And then 1/4 is just a constant. So there were no z's to substitute. Okay, so now I have the components of my vector field written in terms of t. Now you're ready to take a dot product, and you all know how to take dot products. So you're going to take -1/2 cos and multiply it with negative sine t. Plus, then take the next component of your vector field, -1/2 sine, and multiply him with the second component of the velocity vector, which is cos, plus the 1/4 multiplied with 1. This whole mess, you're eventually going to integrate it with respect to time t. And I would clean it up before you integrate. Sometimes you get lucky, you get some like terms, you know, simplify it a little bit. And this one, check it out. This term here, since a negative times a negative is a positive, ends up adding with the second component, adding up to what?
0.
0. Wow, does that always happen? No. But if it does, heck, take advantage. So what's the only thing we have to worry about that's still left? Well, the 1/4 didn't cancel. So we're just integrating 1/4 with respect to time t, and that's super easy. And heck, any self-respecting Calc 1 student could do that. And work done is 3 pi 4. So they didn't give us any units, so we don't know what the ultimate units of this work is. If they did give you some information, like if you took a physics class, could be joules, could be Newton meters, could be foot pounds, but we don't have enough information to say here, so we'll just leave it. Okay, so there's the amount of work done on this little fly as he buzzes around in the corresponding vector field. Questions?
Wow.
Wow, that was awesome. Do you guys see me as far as video at all or not?
I do see you.
Okay, because I'm seeing me and I'm not seeing my video. Are you seeing me as a live person or are you seeing my profile?
No, I see you.
We see.
No, I see you.
That's just weird. I'm not getting that on my end. Okay. Strange. Okay. All right. So now let's do a little different kind of take. What would happen if we oriented our curves differently and parameterize them differently, and we're trying to find work done? So I'm going to do a problem here, example 4, and we'll be able to answer that question when we're done with this. So check out, I'll set up these two letters A and B as far as the graphs, and then we'll do the problems, okay? So, and both of these are pretty easy because they've already parameterized the curves for you. So you don't always get that, but here you do. Okay, fine. So if you graph this vector valued function, and you could use your graphing calculator in parametric mode, at just where X is the first guy and Y would be the second guy, and then set up your window range to be time minimum 0, time max 3. What you'll get is you'll get, oh boy, that didn't go so well. You'll get the starting point is here at the point 4, 0, and then it curves around. It's kind of like, let's see here. It ends at the point 1, 3. Okay, I'll tell you that. And then I got to draw my parabola. I'm not very good at drawing. Okay, like this. That looks pretty sad. That looks really sad. Okay, and the direction is in this direction. So I'll put one arrow. So and that's the orientation. That arrow indicates orientation. So it starts here at 4, 0 and ends up at the point 1, 3. Okay, fine. If you graphed this other vector valued function given by that, and time goes from 1 second to 4 seconds, okay, I'm a real human being. I don't feel like one today. Okay, so then what? So then it's like, okay, if I graph this, when you plug in time equals 1 second, it actually starts at the point 1, 3, and then it's actually the same exact identical parabola as the other guy, believe it or not, and it ends at the point 4, 0. So the orientation is the other direction. Well, we get the same answer when we're calculating work done by this vector field. Now you could graph this vector field. This is this a conservative vector field? No, it's not. So I don't know what I could graph it. Heck, I'm just, shoot, man, sorry. You know, one of the things about living in the pandemic is, do you find yourself really easily distracted? like you're so distracted that, you know, like, oh, there's a shiny object. Woo! You can go over there. I don't know about you, but sometimes I feel like that. So I'm just curious, you know, because now I'm easily distracted in this new age of craziness. So let me just, I just want to see what that vector field looks like. So it's like, really, what do you mean? Well, the way I do this is I'm going to have the XY. Remember, a vector field is a very special kind of function. The X function, the M, if you will, is Y. Oops, I didn't put an equals in there. Sorry. No, this is, I got it back up. Equals, got to do this right. So your M is a Y and your N is an X squared. Okay. And then I can graph this funky vector field. All right, let's just see here. Whoa, okay, hang on. Let me get this up here. Let me get this out of the way. Okay, so this vector field, oh, kind of looks like little dots when you're close to the origin. So that's not really interesting. But when you get further and further away from the origin, the arrows seem to get larger and larger. And wow, that's really weird. And what if I zoomed out some? Let's see, zoom out, see what happens. Huh. It's not that interesting of a vector field. So over here, the arrows kind of, it looks like the arrows are primarily going upwards. Okay, that's interesting. That makes sense because of the x squared. Okay, cool. So power outage for a bit in our neighborhood. Oh my God, Vanessa, that's terrible. Jordan, that happened to you last week and it fried your desktop. Oh my God, that's terrible. I'm sorry to hear that. Let's see if I can get rid of this. Okay, so we have a vector field, bunch of arrows, and what kind of work are we doing here in this vector field? Well, we're going to find out. Okay, so first I'm going to go get r prime because I need it when I'm going to take a dot product with the vector field. So the derivative of 4 minus t is -1. The derivative of 4t minus t squared is 4 minus 2t. Fine. So then the work done, which is this FDR line integral, is going to turn into a regular single integral where t goes from 0 to 3 because they told us that. And then you're going to need to take a dot product, people. And one of the vectors is the velocity vector. But then do not put yx squared here. No, 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 no. I don't want to see any x's and y's going on here. Oh, good God. So what are you going to put? What are you going to put for the y?
That's gonna be
4t minus t squared.
Good, very good. You cherry pick off the y component from your original vector valued curve. And then how about x squared? What goes there?
That's 4 minus t squared.
Yeah, 4 minus t, the x component. Ooh, getting squared. Oh, that really sucks. Okay, then what? Do the dot product before you integrate. Okay, so you're going to have to go, 4t minus t squared times -1. Oh, good God. And then, oh man, 4 minus t, the quantity squared, really? Times 4 minus 2t. Oh, don't make me do this. This is going to kill me. I'm just going to say, et cetera, et cetera. I'll let you multiply it all out. It's going to be kind of a nightmare. But nothing a Calc 1 student can do. Heck, here's what you can do. Just, hey, Calc 1 student, grab somebody who's taking Calc 1 right now, pay him $1. Have them go do this integral for you, okay? And 69 halves, okay? So that's the work done on that. Okay, fine. Then let's do the other problem. So yeah, you're going to need the velocity vector here. Okay, this one isn't as bad. You got a 1 and 4 minus 2t. Fine. So work done on the object as it moves along this curve going in the opposite direction in the same vector field. So you're going to go FDR for this curve, we'll call C2. So you're going to go, okay, time is going from 1 second to 4 seconds this time. So those are the limits on your integral. You still got to take a dot product here before you integrate. And your velocity vector is going to be one of those vectors. It's 4 minus 2t. And then your vector field is, we're still using the same vector field up here with the components y and x squared, but be careful. What do you put for the y this time?
T.
The y.
Sorry, that's 4t squared.
Yeah, you want to do the y component from your vector valued function. So it's going to be 4t minus t squared, comma, and then the force field has x squared, but I don't want you putting x squared here. Oh, no, 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 no. Like, do not go, oh, x squared. You better not have any x's or y's here in this line integral. And you're going to substitute for x squared what instead?
T squared.
Yeah, you're going to go, oh, the t and then square. Okay, then you're going to actually do the dot product. Okay, so 4t minus t squared times 1. Oh, that's not too bad. Plus the t squared times the other component. Oh, boy. 4 minus 2t, and you're gonna clean this up before you integrate with respect to time t. And once again, go call your buddy who's taking Calc 1, pay him another $1 and have him do this for you. Negative 69 halves is the work done. Oh, is work allowed to be negative? Oh yeah, absolutely. Work can be positive, negative, or 0. Go talk to a physics person. They'll tell you that's true. Okay. So what did you get from this example? What is the effects of orientation on getting work done? Do you see that the direction does affect your answer? How?
The sign.
Yeah. So when you orient your curve in an opposite direction, the work will change sign. The parameterization will have no effect. Like if you parameterize your curve one way, as long as it's a direct match for the exact curve, it's not going to affect your answer at all. That won't have any bearing. Okay. So I'm going to have you guys try one right now. I know we only have like 10 minutes left, but heck, let's have you do this one. And this one's easy. Come on, you don't have any parameterization to do. So you're going to evaluate this line integral. You have a vector field there. They're giving you the curve. They even gave you the time limits. So you and a buddy do this problem, okay? And you're basically finding work done because you're using one of these work line integrals, okay? So I'm going to open up the same breakout rooms. Go join your buddy. See you later.
That's straightforward.
Yeah.
Yep.
Yes.
Okay, so hopefully what you ended up doing, because now you really know the deal on this, is you found your R prime, right? Now-
Professor,
Share your screen.
share screen.
Oh, I forgot to share screen. My bad. Sorry. I got to get used to this. Come on, share screen. Yeah. Okay. There we go. Did you guys like my meme? I thought it was pretty funny. Nobody said anything.
Bad luck, Brian.
Yeah. I love that one. You know, I've actually had students who, you know, try to go above and beyond and like talk about concepts they have no clue about. I had one kid, you know, he was like getting out of pre-calc and he wanted to shop for a calculus 2 instructor early. And he hadn't even really finished his calc 1. And I'm like, and he started telling me about all the indeterminate forms in calc 2. And I'm like, you know, it might be better if you took calc 1 first and finished that. And then he goes, oh, well, I don't like you. And he went and wrote me a really nasty email and told me how I'm a very discouraging person. Okay.
I thought that was Ron from Happy Days.
I don't know who it is. It doesn't matter to me, but here's the thing. You want to turn this line integral into an integral you can do business with. So you're going to take a dot product of your vector field with your velocity vector. So the only problem is you got x, y, x, z, y, z. So you're going to have to go x, y is t times t squared, which is t cubed. X, z is t times 2t. And y, z, oh man, is t squared 2t, right? And this is going to be kind of a mess. So when you do your dot product, t cubed times 1, well, that's t cubed. This is 2t squared times 2t. I think I'm going to get 4t cubed. This is t squared times 2t, so that's really 2t cubed multiplied with 2. That looks like it's going to be 4t cubed. Hey, good news. These are all t cubed terms. Fantastic. So why don't I just add them all up before I integrate? Fine. So I have 9t cubed dt, and that's just going to be 9/4 t to the 4th. Evaluate between 0 and 1. And I hope everybody got 9/4. Is that true?
Yes, ma'am.
Okay. And if you didn't, I don't know, find out what the heck you did wrong there and, you know, go. So here's what I want to say. Have a great weekend. I have office hours from noon to 2 today. If you have any last minute questions or homeworks or you want to look at the quiz again, I'd be happy to help you. So you got a midterm Monday. I'm not going to see you. There's no Zoom. I'll see you guys on Wednesday if I don't see you for my office hours today. Okay. Good luck on your exam.
Thank you.
Thank you, Professor.
Take it easy.
Thank you.